Okay, let's do this. So I'm working in your notes. We're beginning with testing the difference between two proportions. This is the test statistic for testing a difference in two population proportions. This test statistic was used in the notes on Canvas that works through an example for testing the difference between two proportions. In terms of the assumptions here, we have a categorical response for two groups. These are independent random samples. The sample sizes are large enough so that we meet this criteria, that NP and NQ are both larger than 5. And the null hypothesis is always the difference is 0. That's equivalent to saying, this is the same as saying P1 is equal to P2. The proportion of interest for one population is the same as the proportion for the other population. So the alternative hypothesis, the alternative hypotheses could be P1 not equal to P2, P1 less than P2, or P1 greater than P2. The test statistic is here. Again, it was used in the test on Canvas, and the standard error, which you don't need to worry about, it's really just a formula, is here. Okay, so let's get into it. So here we have an example of, let's see, in a sample of 200 workers, 45% said they missed work because of a personal illness. Gee, that seems apropos. 10 years ago, in a sample of 200 workers, 35% said they missed work because of a personal illness. At alpha equal to 0.01, is there a difference in the proportion? Okay, so we do want to identify the two groups. So I'll let P1 be the current group. And P2 is, P2 is the population of group from 10 years ago. And the parameters in this case are, there's so many P's floating around in this work. P1 is the proportion of workers who missed work due to personal illness from, from population 1. And P2 is the proportion who missed work from population 2. Okay, now in terms of the stats, in terms of the statistics, we have point estimates. P1 hat is the proportion of individuals who missed work from population 1. In other words, that's the current group. So according to what it says here, 45% said they missed work due to personal illness. So this P1 is 0.45. And the point estimate for P2 is 35%, or 0.35. Okay? So now so I think we identified most things. By the way, P1 hat is X1 over N1. We know that P1 hat is 0.45. So we have 0.45 is X1, that's the unknown, over N1, which is 200. So it looks like 200 times 0.45 it looks like X1 is 90. There were 90 people in that first sample that said they missed work due to personal illness. That's in the current group. Now for P2 hat is X2 over N2. So P2 here is 0.35, and that's going to be the number, and that's in the older group. That's in the group from 10 years ago. So that's going to be the number who missed work from 10 years ago over the sample size, which was also 200. So if you just solve for X2, it looks like X2 here is 70. So that's the number of people from the sample in the older sample that said they missed work due to personal illness. Okay, so what's the null and alternative hypothesis here? Well, the null hypothesis is always equality, so P1 is equal to P2. And the alternative hypothesis, well, what are we testing for? Is there a difference? A difference in proportion. So the alternative hypothesis here would just be not equal. Now, in terms of the test statistic, the test statistic is a z-statistic, and that, let's see, oh, I don't have that out here. That is here. So I think in the, you should check on the formula sheet. In the formula sheet, this isn't stated as 0. It's stated as, I forget what, it's something else. Anyway, we're assuming the difference between, under the null hypothesis, the null hypothesis is that the two proportions are the same. So the difference in the proportions is 0. So that's our null hypothesis. I think in the formula sheet, you could do this test if the null hypothesis were a difference other than 0. So the difference between P1 and P2 could be a number other than 0, but you're not going to see that case. Most likely you're not going to see that case. We'll be on the lookout for it, but I think we're not going to see it. So, okay. So anyway, the test statistic then is a z-statistic. That means we're using the z-distribution. And so it's going to be P1 minus P2. Those should be hats here. Yeah, that's not so good. Yeah, those should have been hats, so I just saw there's an error here, so, or well, fix that in your notes. Sorry about that. So that should be P1 hat minus P2 hat. Subtract the value assumed under the null hypothesis. Under the null hypothesis, the difference is assumed to be 0. Then divide that by the standard error. The standard error here is given by this expression. The standard error is involving this, P different type of hat. So P different type of hat is a pooled estimate for the proportion under the assumption that the proportions are actually the same. So this is going to be x1 plus x2 over n1 plus n2. I didn't do that calculation down here. I could do it now. So that's going to be equal to 90 plus 70 over 400. So it looks like 160 over 400. Okay, so that's p hat, and then q, well, special p hat, and then q is 1 minus p. Okay, so this will be the square root of this q, and then 1 over n1. I don't know why I'm rewriting this. That's kind of silly, because there's so little space here. You know what? That's silly. Since it's silly, I'm going to stop. So what I'm going to do is just put in the values that I need for this. That's what I'm going to do. So z is going to be P1 hat, which is 0.45, minus P2 hat, which is 0.35, divided by the square root of P, this one, P overline, which is 160 over 400, which is the same as 16 over 40, times, let's see, 1 minus 16 over 40 sounds like 24 over 40, times 1 over 200 plus 1 over 200. So that's a kind of nasty looking calculation. We can do that calculation very quickly here. If we turn this guy on, let me turn this on, and I go to stat and tests, and I do the, test. I want to do the two proportion Z test. I want choice 6. And in choice 6, we need to identify the number of favorable responses for each of the two populations. So X1 here we've already determined is 90. N1 is 200. X2 is 70. N2 is 200. The alternative hypothesis is not equal. I guess we did one of those earlier today. And then calculate. So you know what? That was a shortcut. I didn't have to do this formula by hand. I'm just using the result here. So it's about 2.041 approximately. So here's the test statistic, and here's the p-value. The p-value is 0.04. Now we're testing this at alpha equal to 0.01. So, this is not less than alpha, so this will be a case of fail to reject. But really, there is some evidence for the alternative hypothesis here because the p-value is less than 0.05. So we'll, incorporate that information into the interpretation. Okay. Now, in terms of running out of space here, whoopsies. Oh, I didn't want that. Okay. Just made it really big. As you can see, there, that's better. But there, I just want to move it up a little bit. Okay, in terms of the critical value, this is being tested at alpha equal to 0.01. So, and it's a Z test. So this is a Z distribution. So it's a standard normal. The mean is at 0. So we want, so alpha, since alpha is 0.01, alpha over 2 is 0.005. So we need the value of Z that puts an area of 0.005 in a tail. And because of the symmetry of this distribution, one of those values is positive and one of those values is negative. You can find that value out. You can determine that value by using inverse norm. I'm going to write a few more digits here before. Oh, well, actually, I don't need to. I already have the p-value. P-value is here, so I'm just going to jot that down. The p-value is about 0.041. Okay. So, if I want to know the critical value, go to distributions, inverse norm, 0.005, and we get 2.576. So this is 2.576. This is negative 2.576. So the test statistic, let's do that in a different color. What color am I in? Let's be there. It's still below. Why is it still below? Because it says pen 2. Oh, darn it. Oh, it's this one. Okay. I'd like to see that it's not. Yeah, yay. Okay, so this is 2.041. So you can see that's O. O. 4. So you can see it's not in the rejection region. So the decision here will be to fail to reject, which we already knew. So the decision is fail to reject H0. Fail to reject H0. So what does that mean? Well, since our p-value is larger than alpha, that is a case of fail to reject, but the p-value is less than 0.05, so that there is some evidence, but not at this level, not at that level. Oops, having fun with this. In favor of the alternative hypothesis. So the interpretation would read as follows. The data gives some evidence because P is about 0.041, which is less than 0.05, but it's, right, but it's, but not at the alpha equal to 0.01 level. So the data gives some evidence, but not at the alpha equal to 0.01 level, that that there is a difference in the two proportions. Okay, so that's it for this one. Hopefully, as I continue doing this online business with the recordings, I'll get better with my pens and stuff.